Good day and welcome to today's class. Our last class, we talked about rules of differentiation, and we have looked at the first rule under the rules of differentiation, which is known as sum and difference rule. You will recall that we say when we have two differentiable functions, u of x and v of x, okay, under the addition and subtraction, okay. So the derivative of this function y means du dx, okay, and this sum and difference will be preserved, okay. So dv dx, okay. So this is what we talk about when we are dealing with sum and difference rule, and we are given several examples of this type of functions and which derivative is this. So today we want to look at the case where if you are given a function whose relationship between the two functions is product, okay. So in this case, what will be the slope of such function? Okay, so just like we have in the sum and difference rule, okay, so can we say that the differential, just like we have it in the sum and difference rule, can we say that the derivative of this with respect to x gives this? Okay, so that this will also preserve product, but the answer to this is no. Okay, this does not equal to this. Okay, so though this was erroneously done by one of the earliest mathematicians when trying to justify the slope of this, whether it will preserve this or not. A simple example to see whether this is not is if you are given two functions, u of x is x, for example, and v of x is x squared. Okay, so if you find the product here, y, which is uv, will be x multiplied by x squared, and this is x cubed. So from here, if we differentiate y with respect to x, this becomes 3x squared. Okay, so that is this right hand side derivative. Okay, so let's see whether derivative of v with respect to x multiplied by derivative of v with respect to x will also give us a similar answer. Okay, so from there, if we find derivative of x, derivative of u with respect to x, this will be 1, and the derivative of v with respect to x gives 2x. Okay, so let's see whether the product of these two also give us, let's see what it gives us. Okay, so therefore du dx multiplied by dv dx is equal to, according to what we have here, du dx is 1 and dv dx is 2x. So we'll multiply this. Let's see whether this gives us. Okay, so if you look at this answer, the multiplication of this two is 2x, okay, which is not equal to this. Okay, and because of that, we'll see that the product, okay, does not, the derivative of the product does not preserve the same thing. Okay, so we can't say this is equal to this, okay, other product. So this is why we need to know what is exactly the product rule. So that is where we are going now. So we label this B product rule. Okay, here we'll say if u of x and v of x are differentiable functions, for which y equal to the product of the two differentiable functions. Okay, So then the slope of y with respect to x is u of x dv dx plus v of x du dx. Okay, so this is the slope of this function where if y is given by the product of two differentiable functions. Okay, so how do we get this? Okay, so let's quickly look at that. Okay, and of course, since u of x and v of x are differentiable, okay, so the derivative also will be differentiable for the value of a given s, except otherwise where the domain will not be the same. So let's see the proof of this. How do we get this? So say proof. Okay, in the statement of the rule, we have if u of x and v of x are two differentiable functions. Okay, so we first of all assume that since that is an antecedent there. Okay, we say suppose u of x and v of x are differentiable. And what it means when we say two functions are differentiable, this means the u of the x is equal to the limit as h tends to 0 u of x plus h minus u of x all over h, and dv dx is equal to the limit as h tends to 0 v of x plus h minus v of x over h. Okay, so this is what we mean when we say u of s and v of s are differentiable. Okay, okay, so such that y equal to u of x v of x. Okay, so yeah, what we are just trying to do is to explain when we say u of s is differentiable. Okay, when we say u of s is differentiable, what it means is that the derivative of that u exists. Okay, same thing for uh, v of x. Okay, which is this. Okay, now we want to look for the derivative of this function, uh, which are a function of two differentiable functions. So now we want to find dy dx, and of course y dx will be equal to u of x v of x. Okay, that is, we are replacing y here with u of x and v of x, and then we can have the definition as follow. Okay, so let's shorten this because of space. Okay, so we can call this u and we'll call this v. Okay, so this will be equal to the limit as h tends to 0 u of x plus h v of x plus h by definition of derivative. Okay, if the derivative is given as u and v. Okay, and this will be u of x v of x all over h. This is the derivative of two product functions. Okay, so furthermore, when we simplify this further, this gives so let's bring this up. So this is equal to the limit as h tends to 0. Okay, just as we have it here. Okay, we are lifting everything here up. Okay, so here I want to introduce a trivial term here. Okay, and the trivial term is u of x plus h v of x plus u of x plus h v of x minus u of x v of x. Okay, so just like we have it here. Okay, this u of x v of x is this. Okay, this time here is a trivial term. We are introducing this. As you can see, this can cancel out. Okay, so everything here is over h. Okay, so the next thing is to group what you have here into 2, and then let's see what we have. Okay, so this becomes, if you look at these two terms, u of x plus h is common, so factor that out. Again here, v of x is also common here, so, and this is a plus. Let's factor the v of x out to have this. Okay, so everything is over h. Okay, so by the law of limit, this limit will affect this term and it also affect this term. Okay, so and this gives the limit as h tends to 0, u of x plus h, v of x plus h minus v of x. Okay, so since the two terms we have here have the same denominator, so we can distribute the denominator on them, so that this will be this plus the limit of v of x, u of x plus h minus u of x, gain everything over h. Okay, so similarly, we can also apply the law of limit under the product. Okay, so this limit will affect this and it also affects this under the law of limit. Okay, so this also becomes okay, so here this h, we are given this h to this place because this term needs this h more than this. Okay, so okay, it will be meaningful to put h under this than putting h there. And also we'll see that this v of s is independent of h, so this limit will not affect this. Okay, so but let us write. Okay, so in our last something, we just bring that as a parametric constant because it is independent of h. Okay, so the limit will also affect this. Again, we are using this h under here. Okay, because it will be meaningful to put h here. Okay, so this becomes this. Okay, so if you apply the limits to this, okay, so this becomes u of x plus 0, and looking at this has a meaning. This means the derivative of v with respect to x, that is this, and also this limit will not affect v of x as we have said earlier. Okay, since this is independent of h, so this becomes v of x, and this also has a meaning. This also means the derivative of u with respect to x. Okay, so in order to write this in the proof form, if you add x to 0, okay, so this becomes okay, x plus 0 is x, so this becomes u of x dv dx. Okay, so as we have it here, so plus v of x du dx. Okay, so this is how we prove the derivative of function of a of a function of product of two differentiable functions. Okay, so we can now consider a few examples to justify the product rule. Okay, so let's consider this example. So if you are asked to differentiate y equal to exponential sine x with respect to this WRT means with respect to x. Okay, that is the argument here is x. So we want to differentiate this. Okay, so accordingly, okay, you will see that these are two product of two terms. We say let u equal to the first function, which is ex, and the v is the second function, which is sine x. So accordingly, if you use the formula, this formula says u, okay, u will come first, then multiply u with the derivative of v with respect to x. And we see that here, if you find the derivative of v, okay, let's write this accordingly. Okay, this is d. Okay, so let's put v there. V here is sine x plus v of x is sine x, and this is multiplying du, and here u is exponential x. Yes. So accordingly, this is exponential x. When we differentiate sine x with respect to x, this gives cos x. And if you also here, if you differentiate exponential x with respect to x, this does not change, it's exponential x. Okay, so we can simplify this further. Since exponential x is common here, we can factor exponential x out, so that this is cos x plus sine x. Okay, so this is the derivative of this function with respect to the argument x. Okay, we'll recall that the function exponential x is differentiable everywhere in the domain of R. Similarly, sine s is also differentiable everywhere in the domain of R. Okay, so if you look at the slope also, exponential is a differentiable function, cos is a differentiable function, sine is a differentiable function. So the addition of two differentiable functions is differentiable. So accordingly, the product of these two also is differentiable everywhere in the domain of R, because there is no point of x for which this slope will be undefined. Okay, so that is how we apply the rule. So let us also consider another example. We'll call this example 2. Okay, so example 2. So differentiate a function y equal to x squared ln x with respect to the argument x. Okay, so here also the first function is u. Let's call it u to be x squared, and v is the function in x. Okay, so according to the formula, this is u dv dx plus v du dx. Okay, so we'll substitute this term into the formula. This is x squared multiplied by the v is ln x. Okay, so what it means is that the time here will be ln x all over dx plus v, which is ln x, multiplied by du dx. Okay, so this is x squared. Okay, so accordingly, we'll differentiate this term has no derivative on it, so it is x squared. So if we differentiate ln x with respect to x, okay, this is 1 over x, okay, plus no derivative on ln x, so this becomes this. Okay, so the derivative of x squared using the power law, this is 2x. Okay, so this becomes one x cancelled out here, so this is x, okay, and this is 2x ln x, okay. So accordingly, this is what we have as a slope of this function. Again, looking at the domain of this function, this is a quadratic equation, a quadratic function, sorry, okay, and it is differentiable everywhere in the domain of R. Okay, but this function is multiplying a logarithm function, which is only differentiable for positive x. Okay, so since these are multiplying one another, okay, we'll say that this function is only differentiable, okay, when x is positive, okay, since they are products, okay, because if you substitute, for example, if you substitute when x is 0 here, this will be 0 square multiplied by ln 0, and a 0 gives negative x. Okay, that is in an undefined term. Okay, an undefined term. So because of that, we say this function is differentiable for when it's. So let's see the slope also. Okay, the slope also gives this. This is a linear function, which is differentiable everywhere in the domain of R. This is also a linear function. But for the fact that this 2x is multiplying in x, okay, the domain of this function is also any number from x greater than 0. That's where the function will be differentiable. Okay, so let's add the last example, and then after this example, we cut the. Okay, so let's have it this way. Okay, let's consider another example. This example will be in a different dimension. Okay, let's say we can use this formula to evaluate slope of different functions. Okay, so evaluate the slope f prime of 3. Okay, given that y, which is same thing as f of x, is equal to x cube v of x, where v of where v of 3 is equal to 2, and v prime of 3 is equal to 1. Okay, so let's see this example using the product rule. Okay, so say solution. Don't forget, we want to evaluate the slope. Okay, at 3, and the function is given as this, where v of 3 is 2 and v prime of 3 is 1. Okay, so accordingly, so dy dx, okay, which is simple as f prime of x, okay, is equal to x squared, okay, multiplied by dv dx, that is the slope of v with respect to x, plus v of x multiplied by d of x squared dx. Okay, according to the formula, you know, this is a u. Okay, sorry, this is x cube. This is x cube. Okay, all right. So when we apply this becomes x cube v